Hi, I'm Hong Kim. I will present the paper Optimal Multiple Importance Sampling. Before we look at the paper, I will talk about some prior technique that will help you understand the paper. First is multiple importance sampling. This appeared briefly in class, so we already know a little. I will explain the MIS by briefly summarizing class material. In light transpose simulation technique, we track ray in the reverse direction and calculate the radiance emitted at a particular point. So, our ultimate goal is to solve the rendering equation so that calculate the radiance from a particular point. But it is difficult to calculate the integral term, so we estimate that value with MC estimator by sampling some domain. Next, in order to reduce the variance of MC estimator, we generate more samples on high values on the underlying function. This is the main idea of importance sampling. And in class, we especially learned about importance sampling for light sources. There are many factors that influence the importance of sampling, such as incoming radiance, PRDF, visibility, and cosine terms. MIS enables combining different sampling techniques that consider each factor in a robust way to form better MC estimator. This is MIS estimator. W is a weighting function indicating importance of each sampling technique. Under that condition, MIS estimator is unbiased for any weighting function. This figure is taken from the paper written below. We can see that combination of sampling is less affected by physical elements than by one sampling. As we can see, MIS improves the robustness of the estimator. Second prior technique is balance and power heuristics. The key to the efficiency of MIS are the weighting functions. The two most commonly used weighting functions are the balance and power heuristics. In prior work, it has been proven that any other weighting function cannot have significantly lower variance than the balance heuristic. Power heuristic is better suited for lower variance problems, that is, those where one PDF pi closely matches the integrand function fx. The last prior technique is control variate. The control variate method is another common variance reduction scheme of MC estimator like MIS. The variance can be reduced by combining the existing estimator with the appropriate new estimator and the appropriate coefficient. I will skip the detailed proof. From now on, I will talk about what has been studied in this paper. The object of this paper is very simple. It is to find the weighting function that minimizes variance of MIS estimator. They focus on weighting function, so they assume that sampling techniques and sampling allocation were already determined. That is, the number of samples and the PDF of each sampling technique were already determined. First, they pointed out an inherent problem of balance and power heuristics. In the graph, the x-axis presents the domain of the sample and the y-axis presents the value of PDF or weighting function. They set one-dimensional integrand function f, and they used three sampling techniques P1, P2, and P3, and one sample is taken from each. Second, third, and fourth columns show each weighting function and show variance at the top of graph. The best technique heuristic weights in first column means using only the best sampling technique with the lowest variance. I will call this one best important sampling. Difference of first law and second law is only P2. In first law, P2 closely matches F. On the other hand, in second law, it is very different. As can be seen from the graph, one best important sampling have the lowest variance, and then it is better than MIS. As I said before, multiple sampling improves the robustness of estimator, but the robustness comes at the expense of decreased overall efficiency. To improve the efficiency of MIS, they looked again at the past paper introducing balance heuristics, and then they found that there was an implicit bound in which the weighting function should be greater than 0. Therefore, they erased this bound so that nothing bounds was left over than those necessary to ensure unbiasedness. So this is final problem to be solved in this paper. And they eventually derived the optimal MIS weights and the optimal MIS estimator as follows. Now, the weighting function may be less than 0 by the negative term of the equation 13. I will skip the detailed mathematical proof. Optimal MIS weights yield estimators with far lower variance than estimators utilizing any of the three heuristics. It even has a much smaller than the minimum variance that estimator can have in the range of difference with variance heuristic in optimal combining sampling techniques for Monte Carlo rendering paper. Now I'm talking about theoretical contributions to optimal MIS weight they induced. The first is that optimal MIS estimator can be interpreted as control per rates. And second is that relation to balance heuristic. We can see that each term of the MIS estimator corresponds to each component of the control variates as follows. The term excluding the first term of the optimal MIS estimator is the estimator sampled with balance heuristics. Also, we can check the optimal estimator's variance is less than or equal to the balance heuristic variance. More importantly, it shows that the balance heuristic is optimal whenever Vg equal to 0. To get estimator f, we should calculate a, b, and alpha. In the actual experiment, the paper calculates these terms one by one. At this time, two estimation methods are proposed. First is progressive estimator is updating A, B, alpha, and F for each iteration. Second is direct estimator is updating only A and B for each iteration and calculating alpha and F at once after iteration. The direct estimator is simpler and more efficient than the progressive one. In each iteration, it only updates the A and B estimates, and the linear system is solved for alpha only once after all iterations have been processed. These show MSE of the progressive and direct estimator versus the overall number of iterations plotted on the log-log scale. When used to estimate the first law and second law integration problem from motivation slide setting. The black line represents the analytically computed variance of MIS estimator with the optimal weight divided by n iterations. Bias of the direction estimator on the log-log scale. The black line in bias graph corresponds to 1 over n, where n is the number of iterations on the horizontal axis. For both A and B cases, we show the correlated and uncorrelated estimator variance. In the correlated case, both progressive and direct estimators have similar performance, almost as good as the reference optimal estimator with a known alpha vector. The direct estimator is biased. We can observe that both the correlated and uncorrelated versions are consistent, with the bias diminishing roughly at O inverse n rate with the total number of iterations. I still well don't understand what is correlated or uncorrelated, so it would be nice to talk together. These figures show equal sample comparison of different weighting functions for a trained light selection technique and defensive techniques. In contrast to the power heuristic, the optimal MIS weights are never worse than any of the techniques alone. The MSE improvement is with respect to the power heuristic combination of the trained and uniform techniques. Thank you for listening to my presentation.